of what we can to simplify the circuit, and then see where we would put the probes from there, based on what values we get from the equivalent resistance.
I think that's pretty much what you'd have to do it that way. But I think you basically, what I was sort of shooting for is, this is all one, that's one, and that's one. So I have 3 different places to put the probes. There, there, and there. And that are the same.
If on the test we drew it, you wouldn't be opposed to it.
No, just so long as you draw it correctly. I think the biggest issues I saw on that particular problem was people putting it here and here. So if you put the probes here and here, what would the resistance be?
0.
Yes. Now, did I state that you have to have at least one resistor between the probes?
Yeah.
Okay.
Can you draw the probes and then go through how to calculate the equivalent resistance?
As you're asking whether you as a student on the test can do that, or whether you wanted me to do that right now?
Yes.
Me, okay. All right, so drawing the probes is, you can put, if there are 2 dots on it, I'm gonna make the assumption that's where your probes are. However, typically, the probe, you just draw lines off of it. Some people attach the battery to it, that was fine. So, if all these are the same resistances, well, this equivalent resistance is half of R. That's half of R. So I've now reduced it down to, I have R over 2, R over 2, R, and I have the probes here and here. Those are now in series if my probes are here, so that would have a resistance of R. So this has now become my R here and then R here. And so this is R over 2. Is the total equivalent resistance if I put it here and here. I've only one other choice in this scenario, because putting the probe here or putting the probe here when this is up here, it doesn't really matter. Or from this point of view over here, we've got, I'm putting the probe on one side of this, and the other one on the other side of this. Or if you prefer that, that's the same thing. But again, this is R over 2, that's R over 2, and that's R. So from this point of view, we basically have R over 2 going this way, R, and then R over 2. These are in series, so we just add those up. So this becomes 1 over, I got R over 2 on this side, and on that side, 3R over 2. Those are in parallel. So 2 over 3R plus 2 over R equals 1 over the equivalent resistance. So it's 8 over 3R. If I did that right, 3, so 6, 2, 4, good. So my equivalent resistance in this scenario is
3/8 R.
Is that what you said? Okay. I heard a different number there, sorry. So this would be maximum, and that would be minimum. Is that what you wanted?
Yeah.
Okay. I feel like when I said, is that what you wanted, it came across as harsh.
Oh, no.
Okay.
I think this equation's plotting current versus time.
Yes.
The old current versus time, so it was resistor, capacitor, both, and then parallel.
I was gonna ask that.
I was gonna ask that one.
I was gonna say-
All right. We have battery, resistor, battery, capacitor, battery, and then resistor and capacitor in series. Then battery, resistor and capacitor in parallel. I think I got those right. Now, in each of the cases, I think it starts out that are uncharged. Assume each power supply is ideal and is identical to the other power supplies. Each resistor is identical to the other resistors. Each capacitor is identical to the other capacitors. All time begins the moment the circuit is completed. In other words, all of the graphs begin at the origin. If there are two graphs which are similar, you need to differentiate them. For example, if one, and then I give an example of what it means to differentiate. Yeah, remember this one, at least parts of this one. Not many people started them at the origin. Or not enough people, but they all start at the origin. So at least I got that point down. So if I just have a resistor in here, what do we know about the current flowing through a one resistor circuit? Why?
It's resisting the current.
It is resisting the current. However, when you were doing your Ohm's law labs, did you take into account that the current was decreasing?
Not really, I don't think so.
What assumption did you make?
Well, I was saying that they were like getting heated up, so like every single time we were connecting them, there was more heat that was coming through the resistor, and as they're heating up, the resistance was increasing, so then our charge was decreasing.
Okay.
Which is why all the values were less than the ideal values. Like every experimental value was always less than the ideal value that we calculated.
Did you touch the resistors to see if they were heating up?
No.
Okay. I actually wasn't considering the change in the temperature, which would change the resistance. So, assuming the resistance is constant, what would you say about the current? We're not worried about heat issues.
I guess it would also remain constant.
I hope so. Now, if it does heat up, that was something I did not take into account, and I hope if somebody had considered that, they would have come back and said, wait a second, isn't it heating up? No one did. But, so I know it's gonna be constant at some point. It starts at 0, it does get to constant, and so, it very quickly gets there. It's gonna be something like that. This is current versus time. If you do bring in the heating effect, because the resistors are taking energy out of it, every time the current goes, particles go through the wire, they bump into things, there is an exchange of potential and kinetic energy, and so if the particles will move a little bit faster, it will heat up, resistance will increase, and therefore, over the long run, if you do take that into account, it would drop off. Whether it's linear or a steep drop off, I suspect what would happen is that it would start out somewhat linear, and then as it gets hotter, it's gonna reach some point where it obviously curving, but I don't know, I haven't played around with
I
that.
think I think it's parabolic in nature.
Okay.
There's a formula for how much like heat is created, like the heat index that's created when it's running through the current. And I think that formula is parabolic.
Okay.
So I'd assume maybe.
I've seen the one for resistivity. The resistivity changes as the temperature goes up. I'm thinking that's linear, but it also would probably depend upon how quickly you can dissipate the heat, because it's generating heat. If it's a breezy day, the heat would go away faster, and so you probably would keep the resistor cooler.
Also, the type of circuit board that's mounted to.
Okay.
It makes a big difference in the temperature.
Let's just simplify it and say we're not worried about the heat.
Okay.
All right, with a capacitor though, what happens when the capacitor is full? Or close enough? If you can't put any more charge, any noticeable amount of charge on the capacitor, what happens to the current?
Does it go the opposite way?
Through the battery?
Never mind.
If it starts going the opposite way, you probably need a new battery. Because the barrier between the positive and negative charges is broken down. Or think about it, you make the connection, you make the connection, start at 0. And suddenly we have electrons start floating around onto this plate, driving electrons off of that plate. The more electrons that get on this plate, the harder it is to put another electron there.
So the current will go down.
So the current would drop off. So you would, when you first started, you do have some peak current that starts out initially, well, right after 0. It does peak, and then it starts dropping off. Now, we're not putting numbers on this because you really can't do numbers without more information, but this happens, it gets to here fairly quickly for a standard capacitor. But it also depends on how much capacitance there is. So what effect does the resistor have? So if we think about this one right here, except now we've thrown a resistor into it, what does the resistor do to the current flow?
Keeps it constant. Well,
Prevents.
would it would kind of balance out the loss of current from the capacitor, right? Once it's full.
Except the fact that this is in series. I think what a lot of things you just said are going to apply down here,
Okay.
but up here, not so much. Lawson, you said something?
Would they change it at all?
It would change it slightly. And this was the reason why I threw in the, if there's two that look similar, differentiate them somehow.
So it wouldn't reach that peak as quickly, or it'd be more of a curve.
Yeah. And so it is similar, it's still going to charge up the capacitor, and when the capacitor is full, it's going to stop with the current flow, but this is going to slow it down. And so to differentiate it, I drag it out more. And then in the last one, recognize the current, I have current flowing here and I have current flowing that way. So I've got two currents. My capacitor is still going to get filled up. And so at some point, this is going to drop off. But then I'll just have my steady current here. So going along with pretty much all that Austin said earlier, except applying it to here, it basically is these two added together.
So it's like the capacitor is the one where it like reaches the peak and then starts to drop off, but because the current has multiple ways to go, it balances out.
Yeah. And so what you'll end up with, depends on what you mean by balances out, but you end up with, you know, you get to start the very steep rise at the
Yeah.
beginning, and then it falls off
Yeah.
at not at 0. Other questions about this one? Other questions? Jesse?
How do we know it's wrong?
spring 14, okay.
Question 11 and calculus problem. Go on to that one.
Yeah, that probably would, help me. Thank you. There exist two conductors charged to capacity. Apparently parallel plates. So one at x equals 0 and one at 2 meters. The plate has a maximum charge of negative 23 coulombs, and this is a maximum charge of positive 23 coulombs. That's convenient. And then we've got something in between so that the electric field is described by negative 3x squared minus 2 over x plus 1 I hat. That's the I hat direction. I assume all variables are in SI units. And I probably threw that in there because I didn't feel like actually figuring out what the units were. So the first question is, what is delta V from the negative to positive plate? And then what is the capacitance? Thank you. Well, the capacitance is the charge divided by delta V. So once I have the voltage between the plates, I can find the capacitance just by 23 coulombs divided by whatever my answer to part A is. So this question is, in essence, asking the relationship between the electric field and the potential difference. Now, if the electric field is constant, if you need some way of sort of keeping track of it, that's if the electric field is constant, but the electric field is not constant, so we do have to use some calculus here. So delta V is negative integral of E dot dx. And we're going from the negative plate to the positive plate. So we're going from 0 to 2. Now, another reason why I made the distance between the plates so large, one, you're dealing with nicer numbers, potentially, but also I did not want to give the illusion that we can assume infinite plates. And I don't know how much of this I actually have posted and how much of this is just on my own hard drive. This is spring 2014. That's the year, and then spring is 1/01, summer is 02, fall is 03, in case you have ever wondered.
I think you told us that when you had it, yeah.
And I apologize.
How to name documents.
Ah, that's right. I did at that point. So this is just basically integral from 0 to 2 of negative 3x squared minus 2 over x plus 1. It's in the I hat direction. I don't think I stated this, and I should have. I hat assumed is in the positive x direction, and so therefore this is just times dx. Because this right here, dx, is I hat dx. So dot product, same direction, just multiply. So like components. And so this becomes the integral from 0 to 2 of 3x squared plus 2 over x plus 1 dx. And so we get x cubed from 0 to 2 plus 2 natural log of x plus 1 from 0 to 2.
Explain one more time why we were able to drop off the negative sign.
I distributed.
Okay.
Yeah, nothing fancy there.
Yeah, I didn't notice it, so.
Minus signs are the bane of existence. It was a little, it was, I think the ancient Greeks didn't deal with them, or maybe that was just fractions.
Did you want to record all this?
It's not recording?
It's not.
Oh, no.
No, it is recording.
Oh, it's
Yeah, the black dot means that it's moving.
usually like when I look at the timer thing's up at the top.
Ah, yeah, no, we're good here. Yeah, sometimes it's at the top, sometimes at the bottom. I wonder if I turn it around, it'd be at the top.
Yeah.
But no, we're
Sorry
good.
about that.
We're good. No.
I was about to say, we're gonna have to redo all of this.
Take two.
The other day, I was in my office, I just finished class, and Assassin comes in with the camera, and it was on pause, and I thought, oh man, if I had the entire class on pause, turned out I had recorded it. Either she hit pause, or I did when I went to hit stop. I thought I was gonna have to redo the whole thing. Alright, so this becomes 8 plus 2 times the natural log of 3 minus the natural log of 1. Natural log of 1 is 0. So this becomes 8 plus 2 natural log of 3, which is some number that will just make your life that much better.
7.38.
What is it again?
7.386.3.
Should we just leave it as, or no, we should just leave it quickly, because you need to calculate capacitance. Never mind.
Alright. Now notice that if I did this correctly, I integrated from 0 to 2, from the negative plate to the positive plate. I should have gotten a positive voltage, and I do. So something went right. So that's the answer to part A, and then part B is just gonna be 23 divided by 7.386.
Why is it 7?
Pardon?
Why is it 7? Because it's 8 plus that.
Oh, did I miss here, or did somebody misinform me? Is that just the second part?
It should be 10.197.
10.197.
197.
Come on, man.
Just seeing if I believe anything. Or did I miss here, or did somebody misinform me?
I'm guessing it was misinformed.
Or am I just hearing voices in my head?
All the above.
Yeah. People start hearing voices in their head. Do they at some point go, is that real? Or is it automatically, does it sound like someone's in the room with them?
That's creepy.
It probably sounds a lot like someone actually talking to them, because all your sensory stuff is in your brain, so.
Okay.
I know what I did wrong. I differentiated. Not doing.
Ah, okay. Yeah, the math people tell me there's a huge difference between that. And so this ends up being 2 point something. There, right. An answer so controversial, Jesse had to leave. Any other questions about this fabulous problem? All right. So, any others? Any other questions? Yes, questions?
2B. Just
Or not.
Two.
Students going to make parallel plate capacitor from, Yeah, this was the parallel plate capacitor lab. If I had my wits more about me, the lab that you would have done would have been the one where you make your own capacitor. Instead, I gave you the COVID edition, which was done at home, and I figured most people don't have ohm meters or capacitance meters at home. All right. Ideal capacitance of capacitor. Oh, I guess there is some detailing I'm gonna need. Because usually when people make their capacitor with a sheet of aluminum foil, they do it the part A way, where they basically have this piece of aluminum foil, and they cut it in half. And this was 1.2 meters and 4.5 meters. And I think that's all the information the dielectric is 0.1 millimeters thick. Dielectric constant
Spring
of 2.
2015. Number 2.
You said spring what?
2015.
So 1501, problem number 2. Thank you. All right, so even though you asked for part A, let's take a look at B. Or, even though you asked for part B, let's take a look at A. So cut it in half, you basically now have sheets that are gonna be 1.2 by 2.25 meters in size. You have a dielectric in between them, very similar to what you did with the two plates that you used, except you got a much bigger piece of aluminum foil. You roll it tightly because you want them pressed as close together as possible. Most of you noticed, if not all of you, that you had a much higher capacitance when the two pieces, when the two plates were closer to each other. So thin capacitance is kappa epsilon sub naught A over D. So 2 times 8.85 times 10 to the negative 12 times the area of whatever that times that is. So 2.95. Tell someone correct me. 0.00.
It's 2.7.
2.7. Probably the biggest mistake I see students make here is forgetting to put this in meters. And you'll get some number for capacitance. And what is this?
4.779 times 10 to the negative 7.
Negative 7?
Mm-hmm.
Carrots.
And wouldn't it just be 0.001 at the bottom?
Oh, it's 0.1
Oh,
millimeters
point.
thick.
Oh, I was just going off of 1. Okay.
I think I read that correctly. It's 0.1 millimeter thickness? Yeah.
Yeah.
Woo! I wasn't wrong about something. Got it as a win. All right, so the second part was the part that I found more interesting. In fact, no student has done this yet, where you take this same sheet of paper, except this time you cut it into 1/3 and 2/3. So this is 1.5 meters, this is 3 meters, this is 1.2 meters. And you take this, the 2/3 section, and you fold it. And you take that 1/3 and you put it in the middle. There's a dielectric in between. So that the metals don't touch. And then you're going to attach your probes to that. So the question is, what is this? How can we make it look like stuff that you've done already? Well, if we think about this middle one as basically two pieces of aluminum foil pressed tightly together. So therefore I've got one on the outside. I got the two that are pressed tightly together. There's no gap in between, but I'm just sort of writing it that way. And then you have this. So this belongs to that piece, this belongs to that piece, and that is the 1/3. These have the same charge on them. These have the same charge on them. In essence, what we have is a parallel capacitor. So I can treat this as that. Now, the size of each capacitor is not the same. It's not the same as it was before. This is a 1.2 by 1.5. and this is a 1.2 by 1.5. So we can find the capacitor of one of them using the exact same formula. So the capacitor of one of them is 2 times 8.85 times 10 to the negative 12 times, like area, 1.2 times 1.5.
1.8.
Divided by the distance between them, still using the same dielectric, 0.0001.
Times 10 to the negative 7 farads.
So the capacitor of one of them is less than what we did the first time, however, they are in parallel, so the total capacitance is just that plus itself. So my total capacitance is 6.36 times 10 to the negative 7th farad. So I actually get a bigger capacitor by splitting it that way. And I don't know if I succeeded, but part of my goal of asking this on the test question was I was hoping some of the students would go, oh, we could have done it that way. If they did think it, they didn't express it to me. And then I think there's a follow-up question of, what is the maximum capacitance you could get from a piece of aluminum foil? And I started going down that path at one point, and then realized, oh, now we have to take into account the thickness. At some point, you have to take into account the fact that you're losing a little bit of aluminum foil every time because of the dielectric in between. And then I probably had to grade papers or something, that I stopped that investigation. It's gonna show up on the test one day, not yours, just to let you know, but it'll show up on the test one day. Other questions about this one? All right, other questions?